All right, good morning, good afternoon, good evening, wherever you're at. Hope you're doing great. Looking forward to going through this next section with you guys, section 9.5, and talking about tangents. Now, a tangent line, I know you've heard of tangents before. We worked with trig functions before, but we are going to look at what a tangent is to a circle, and I'll explain that in a second. So, if you read along the first paragraph with me, I'm going to highlight a couple of things, and then we'll go over to the diagram off to the right, and we'll kind of do some markings there to understand why things occur the way they occur. So it says a tangent to a circle intersects, okay, that's kind of important, circle exactly 1 point. All right, so maybe circle this, exactly 1 point. It touches that circle at 1 point, called the point of tangency. There are important relationships involving tangents. A common tangent is a line, array, or segment that is tangent to two circles in the same plane. I don't think that last sentence is that important. Okay. Now it says here, well, actually, instead of reading the next two parts, if you want to read them, you can. But what I'd like to do next is I would like to take a look at this diagram and kind of understand what happens with the tangent line. Okay. So right now, what we understand is that if this is a point of tangency, that segment or that line intersects this circle at only 1 point, right there and right there. That's the only point that it touches on that circle. Now, if you think about it, how many points make up a circle? There's an infinite number of points. Okay, there are billions and trillions of points that could make up a circle, and we're saying that the tangent line only touches exactly one of them. Okay. Now, what I'd like you to do, I want you to think about this with me. If we have an infinite number of points along the circle here, okay, and the tangent line touches only one of them, the radius to that point actually has a special relationship, and you can kind of see that right here. And that's this, that angle that's being formed with that tangent line and that point is actually going to be a right angle, okay? It'll be a right angle every time. So what I'd like you to do on your paper there is to go ahead and draw on that one and show that this will be a right angle as well, okay? And so if you look at the first bullet point off to the left over there, it says a line is tangent to a circle if and only if it is perpendicular. I would circle that. Remember, perpendicular means right angle to a radius at its point of tangency, okay? So if I was to go ahead and take this line right here, okay, and move it in some way, let's say I move point S up in here and draw that line, tangent line this way, then that radius would have to rotate over and would still form a right angle with that new line, okay? So there's always a radius at that point of tangency that forms a right angle. Now, there's also something else that takes place with this. And in order to understand this relationship, I'd like you to go ahead and draw that line in right there, okay? Yes, we're going back to triangles here, and we're going to do a little mini proof. But I want you to think about what else within those two triangles has to be congruent. Now, as I look at this, and I'm going to make this just a little bit smaller, okay? As I look at this, I see that PR and PT are congruent. The radii are the same, right? As I rotate that radius around, it still remains the same length. I also see that PS is congruent to itself by the reflexive property. And so, as you think about that, those two triangles, they are congruent to each other. And so maybe I'll make a little note of that. I have triangle PRS, I'll do RPS, rock, paper, scissors, is congruent to triangle TPS by hypotenuse leg. Hypotenuse leg. I can write the L there. L. Hypotenuse leg. You can see that there. We have two legs congruent, and we have two hypotenuses that are the same length. Okay? Now, because of this relationship here, something else is going to happen with these tangent lines. Okay, so I'm going to put down therefore, that's what those three dots mean. Therefore, I would then know what about segments RS and segments ST? Well, if you guessed it, they are congruent, which is correct. Why? And again, we're reviewing this. CP, CTC. Those corresponding parts, those two segments correspond of congruent triangles are congruent, okay? Now, keeping this in mind, folks, let me go ahead and give you another quick illustration that might help you. I'm going to pull out my handy dandy compass here, and I'm going to place that. Oh, let's rotate this guy a little bit. Let's change my color. And let's actually measure this length right here. Okay? That's the length of ST approximately. And I think I'm right on it. Pretty close. There's the length of ST. Okay? Now if I go ahead and show that length there, look at that. The length of ST and RT are the exact same. Okay? So if it helps you to visualize this a little bit, think about taking this length and just rotating it over, okay? And those two lengths have to be the same length, okay? So as you read the next bullet point, it says if two segments from the same exterior point are tangent to a circle, then they are congruent to each other, okay? They have to be the exact same length. Now, over the next couple of minutes, what I want to do is just continue to look at these problems. Oh, that may be getting too much. Look at these problems that apply the information that we just talked about. Okay? So let's go ahead and take a look here at number 1. We'll look at numbers 1 and 2. Okay? If you think about it, what should the equation be? Well, if I were to go ahead and take my compass again, place it right here, it would rotate around right to right there. Okay, and what I'm trying to show you again is that CB is congruent to CB. Those two lines are tangent to the circle, therefore they have to be congruent to each other. And in fact, if you look at it this way, maybe this would help too. This forms an isosceles triangle. Okay, if I draw that BD line segment in there. So as a result, I'm going to go ahead and do this. Those are equal. And so therefore I know X has to be equal to 4 if I subtract 3 from both sides. Okay. Now, a problem like number 2, I'm probably going to say, hey, what type of angle is this? Well, the answer is it's a right angle, right? And so, knowing that it's a right angle, I can go ahead and set up my Pythagorean theorem. And I can go ahead and solve for X then, okay? I'll tell you this, X is going to be a whole number, and I'll let you finish that one up, okay? Now, let's actually go to the next page. And let's look at number 4 together. Okay, again, these continue to get a little bit more difficult with each problem here. And in this one, like the last one, I think I'm going to go ahead and just say, hey, it's going to be a right angle right there. Okay? And as I look at this, I can set up my Pythagorean theorem, but the only problem is this. We don't know what this whole length is going to be. Okay? Now, you can do one of two things. I'll tell you both situations, and I'll let you choose. It doesn't matter. In this situation, what's the length of RU? The length of RU is going to be 15. Okay? And so one way to do this is to go ahead and say, hey, the length of this hypotenuse has to be 15 plus x. That's one way to do it. So you could do your Pythagorean theorem again. Leg squared plus leg squared equals the hypotenuse squared. Okay. And right there, I'm probably going to go ahead and plug that into Desmos and solve for x. Okay. But I think there's an even easier way to do this, and that's this. I'm going to go ahead and say that instead of using x, I'm going to solve it in terms of y. Because if I use that in terms of y, again, leg squared plus leg squared equals the hypotenuse squared, If I can solve that equation right there in terms of y, what are we going to do to get x? Well, since y is equal to 15 plus x, probably shouldn't have erased that. Y is equal to 15 plus x. All we have to do is take whatever the y value is here and subtract 15, and that'll give you your x value. Okay? So again, you can do either one, but I'm going to tell you right now, if you were to work this one out, it's got some really neat math in there, but at the same time it's a little more complicated. And so I would do it in terms of y. I think it's a lot easier. Okay? For number 5, we have kind of the same situation. We have a right angle, but we don't know what that length is. Okay? Now, I want you to be thinking to yourself, what is the length of AY? Well, AY is a radius, right? So AY has to be 21. So in the end, 21 plus 8 is 29. And so the Pythagorean theorem can be set up like this. And you can go ahead and solve for x. Okay? So little tidbits here and there, setting up what we know to be true, and then you can go ahead and solve. I'm going to let you finish those problems, and then I want to take a look at the next section here. So if you want to pause your computer and work through those, that's fine with me, but I do want to continue to move on. So circumscribed polygons. The other day we talked about inscribed, when it's inside the figure. Circumscribed, remember, means when it's outside the figure, when the sides touch. So if I were you, I would kind of highlight this whole statement here, okay? Read through that, make sure we understand what's going on. Circumscribed when it's on the outside, inscribed when it's on the inside, okay? So yeah, read through that, make sure you're familiar with that. Let's go to the next problem that I want to work through. Okay. And let's start with, I think it's number 1 I want to look at with you. Nope. Oh wait. Let's just pick some out here. I think we can do maybe number 1 and maybe number 5. We'll look at those two problems together and then be done. Okay. So in number 1, it says here, find the value of x and then find the perimeter. Okay, we're going to do both of these here. Now, what I want you to remember is this. We're going to apply one of the rules we had earlier on. That rule is this. We have a point on the exterior of the circle. We have 2 lines that are tangent to the circle. These are all these lines that look tangent. They are. And so this is a length of 10 right here. If I look at the other side of this line where it touches, where it's tangent, what do you think this length has to be right here? Well, remember, if we rotate that over, that's going to be a length of 10 as well. Okay? Well, as of right now, I already know what x is going to be. It's going to be the sum of those 2 segment lengths. So x is 23. Okay? So that's part of my answer right there. Okay? Now, to figure out what the other value, what the perimeter is going to be, I have to continue this same thought process on around. Make that smaller, make it more precise. So if I take this 17 and rotate it around, this length is 17 here. And if I take this 13 and rotate it around, this is 13 right here. Okay? And so as a result, Katie, give me about 10 minutes. Okay. I'm going to take the perimeter here. If I add up all the sides, here I have 27. Here I have 30. And then here, as we said before, we have 23. And so the overall perimeter, would that be 80? I'm going to put down 80 units. There you go. Okay. So number 1, that's the overall perimeter right there. If we continue down to number 5, and if you have this down, you don't have to watch the rest of this. I'm just going to continue to reiterate what we're doing here in number 5. Again, we have a figure on the outside, circumscribed, and we're going to find the value of x in the perimeter. Okay. So as I start by looking at this length right here is 1. So if I rotate that around, okay, this is going to be a 1 right there. If I start here with 3, this length 3, rotate this around, oh, didn't go. maybe. This is also 3. Oh, 13, also 3. Okay? Start with 2, rotate that around. That's going to be 2 there. And if this is 6, rotate this around. This will be 6 right here. Okay? Not sure why that was there. Okay? So from there, I know that x has to be 8, the sum of 6 and 2. So x equals 8. Okay? That would be in units. All right? To get the perimeter, against the distance around on the outside, so we have 8 plus 7 plus 4 plus 5. And in the end, 24, I believe. Let me check, yep. Units is my perimeter, okay? Hey, you've been a great audience. I hope that was pretty painless. What I'd like you to do is finish up the rest of those problems, and I think finishing up the homework on the back side of this paper here, page 682, isn't going to be too bad as well. I will post the answers on Schoology, and you guys can let me know if you have any questions come Monday. So again, thank you for watching this video, and I hope it was helpful. Good night.